All right. So you guys saw that there's another homework assignment there for you. And once again, there's a pretty good problem that is using linear algebra ideas, matrix ideas, to show you how to treat the waves that we've been doing, well, the free wave stuff. And then there's a couple of shorties, and then there is a problem that is the two Dirac delta well version of what we've been doing. So adding the second Dirac delta does make it more complicated. You can find the solution lots of places, but the goal is for you now to work out a problem of the same nature of what we've been working out. So if you have questions, once again, go ahead and call me or email me. I will be, it's due Wednesday. I was going to say Thursday and Friday I won't be available because going to the funeral, but that's after it's due. So if you've got questions, go ahead. Feel free to contact me because it's not super easy. For quantum mechanics, that means it's not easy. So picking up where we were last class period, we looked at a particle that has a delta function potential, and we looked at the Schrodinger equation, and in solving that Schrodinger equation, we said, okay, we have a boundary. Question?
Do you by chance have the screen projection on?
I hit the button. Let me do it again. Did it change?
There you go.
Okay. It probably didn't work because I hit it before I had my tablet turned on. Thank you for bringing that out instead of waiting to the end of class and saying, we couldn't see anything you did. I mean, it is one way to not be responsible. I didn't learn anything in class because I couldn't see anything he did. I just heard his words, and they were all garbled. So we treated this as having two regions, one on the left side of the delta function, one on the right side of the delta function. So we found the solution in each region, and then we have to match boundary conditions. So on each side of the delta is just 0, right? It's only at x equals 0 that the delta function is not 0. And so our Schrodinger equation became this, it became this shorty. And then we simply defined kappa to make it easier to write. So this part to the right here is just setting, I hate it when I miss, saying this here equal to kappa squared, so it's easier to write. And so kappa is the square root of, notice the minus sign is in there because E is negative. This was for negative energies. And we had, the solution has to have this form. So we put that form into the Schrodinger equation, find the second derivative, and found that we had two solutions, one with beta is equal to plus kappa, one with beta is equal to minus kappa. So our solution, both on the left side and the right side, has this form. So the way that the book chose to name them, and now that we're 2 days past the first time I did it, I will simply go with the way the book chose to name them and not worry about it. So the book chose those for the constants to take the the positive and negative exponent solutions. But then to be normalizable, it cannot blow up as x approaches plus or minus infinity. And since this term here blows up as x approaches plus or minus infinity, in this case, minus infinity, then we had the requirement that A had to be 0. And likewise, looking at the right side solution, is that your lights?
Yeah, they're automatic lights, so every once in a while they just go out.
Yes. We have those in our building. By now, we'll be seeing a faculty meeting. We're all talking, the lights go out, and we're all going like this.
Yeah, same.
Okay, on the right-hand side, because the e to the plus kappa x is going to infinity as x approaches infinity, then g has to be 0. And so we're left with the simple left-hand side, b e to the kappa x, right-hand side, f equal to minus kappa x, which brings us to where we left off. So we have this function, psi, defined in two regions, one on the left-hand side, one on the right-hand side. And then we apply our boundary conditions. First boundary condition is that psi must be continuous. So we have psi at the boundary is equal to psi at the boundary. So I put in 0 because that's where the boundary is. I have the left one and the right one. Now putting in the functions we had, b e to the kappa times 0 must equal f e to the minus kappa times 0. Well, kappa times 0 is 1. Or excuse me, e to the kappa times 0 is 1. And so that means b must be f. Have we found out anything about energy yet? Have we limited kappa? No, we have not limited kappa. So we have no quantum physics yet. We have a solution to the Schrodinger equation, but it's not quantized. But notice I did use the word yet. We have normally two boundary conditions, that the wave function must be continuous and that the slope must be continuous. Plus it has to be normalizable, so that already allows us to kick out two numbers. Now we're going to explore that boundary condition, why it exists, specifically why the slope being continuous normally exists but doesn't exist here. Clearly, there's no way to make that have a slope of 0, or a continuous slope. The slope is clearly discontinuous. So we know we're not going to have a continuous slope with this. What gives? So here is the reason the slope usually is continuous, except in the special case of an infinite boundary. So we start with the Schrodinger equation and we do something completely unexpected. We integrate the equation. Yours times out really quickly if that's the problem. Sure, it's not somebody reaching their hand in, flipping off the switch, saying, ha ha. You'll find Chris Hansen around the door. So we take the integral of the entire Schrodinger equation. So there we go. The integral of the entire Schrodinger equation. And you look at that, and the normal common response is, what's the point? Isn't that a reasonable response? Well, our integral is kind of special. Our integral is going to be about the boundary. So we're integrating about the boundary with limits approaching 0. That is, the width of our integral is approaching 0. So we're going from minus epsilon to plus epsilon, and the limit as epsilon approaches 0. Now, when you do that, it makes the integral kind of easy. Because if you have a continuous function in the limit of integrating over 0 region, what do you have for that function? Okay, I'm going to do it. I'm going to show graphically. I have a function like this, yes. If I'm integrating at this point here where it's continuous, and I have a really, really tiny range, so I'm integrating from, here to here, I'm going to take whatever that height is and multiply it by the width, which is approaching 0, and I get what you said, 0. So under normal circumstances, wow, where's my picture go? Come back to me, there we go. So under normal circumstances, well, if psi is continuous, which it has to be, then this integral is going to be 0 because it's the integral of continuous function over vanishing bound or limits. And if the potential function is continuous, then this one here is also going to be 0. But our case was special. Our case was that the potential function was a delta function. The delta function is infinite at that boundary. And so doing that integral, the integral from minus epsilon to epsilon v psi dx is equal to the integral from minus epsilon to epsilon of alpha times delta of x psi of x dx. And we've seen how to apply the Dirac delta here. What is the integral? Keep in mind that it's going to be, well, you can't forget the constant. It's alpha times psi of 0. Right. So that means that we're going to have a non-zero for that term. Now, finally, this integral here. The integral of the second derivative, by your fundamental theorem of calculus, is going to be the first derivative. It's going to be the difference in the first derivative from one side of the boundary to the other side of the boundary. So notice that this term here was divided out, so it appears over here now. And the minus sign disappeared because this potential had to be moved to there. So, seriously, something is malfunctioning. So what we have in this equation right here is that the limit as epsilon approaches 0 of d psi, because that's plus on the plus epsilon side, it's on the right, dx minus the derivative of psi left, dx at minus epsilon. The limit of the difference in those two has to equal 2m over h bar squared times alpha times psi of 0. The alpha psi 0 is because we just did the integral right there. So this is saying the difference in the slope from one side to the other side is now a finite value instead of 0. So then we put in, since we found that b is equal to f, we'll just have the derivative on the left-hand side is b kappa e to the So there I've actually done the derivatives. Remember that I just took the derivative of this function here and this function here with b equaling f. So the minus sign came down for the right-hand, whoops, for the right-hand side. The right-hand side has the minus coming down. The left-hand side does not. It's good that I went back and checked. So that's continuing on with my calculation. Now we can very quickly solve this. So here's it already written out, just in case I would screw up. Here you can see, yeah, look, my signs are in the correct place now. Applying the limit, those are now e to the zeros, or 1. So I can divide out b e to the 0 from every term. And this is minus 2 kappa equals minus 2m alpha over h bar squared. Divide both sides by 2 and you get what's written down.
Where did the negative on the right side come from?
The negative on the right side came because I forgot. Everything I did was correct except for one thing. My potential function had a minus sign. The potential function was actually minus alpha delta x because it was a negative spike rather than a positive spike.
Okay.
So actually, since I changed that, I have to change this. My work was still fine and dandy. Technically, there's no error. It's just I integrated minus v instead of plus v. And so, yeah, believe me, I thought about that when I got to this slide just now. Hence, I had the ready answer. Since kappa was defined as the square root of minus is that no? Square root of minus 2me over h bar squared, if I remember right. Isn't that what kappa was defined as? It's way back here. Square root 2me over h bar squared, yeah. So we just take this, we square both sides, and we have m squared alpha squared over h bar to the fourth is equal to minus 2me over h bar squared. I'll just write that down. And then you solve that for E. And you get the minus sign, 1m cancels, no alphas cancel, 2 h bars cancel. And that 2 is left down here. So there we now have a quantized system. How many quantum levels do I have for my energy?
What is alpha again?
Alpha was the size of the energy well.
So for one particular system, you only have one energy.
That's right. There's only one energy state allowed. If you make a delta function potential, you only have one energy possible. Last thing we have to do is to normalize. So to normalize this, remember the normalization condition. Was that integral psi star psi from minus infinity to plus infinity. So I had two different regions, the left region and the right region. And so I have to break it into two integrals, one from minus infinity to 0, psi of the left, plus integral from 0 to infinity, psi of the right. And when you do that, you have e to the positive kappa x from minus, or positive kappa x, whole thing squared, so e to the plus 2k kappa x, if you like, from minus infinity to 0, and then e to the minus kappa x from 0 to infinity. Those have to be the same thing because you flip the limits and you change the sign of x, it's the same thing. And so it's just 2 times integral from 0 to infinity b mod squared e to the minus 2 kappa x. Well, integral of e to the minus 2 kappa x is pretty simple. Divide by the derivative of the exponent, so divide by minus 2 kappa, put in our limits, and we have our normalization constant v is just square root of kappa. So we finished the problem. We have a normalized wave function that has matched the boundary conditions and given us a quantized energy state. It's a bound state. It's going to be quantized. It's not scattering. Any questions about this problem? No. Okay, I'm going to jump to the last slide and then come back, because the last slide is looking at our homework problem with the double delta function. So here we have two delta functions, one at x equals minus a and one at x equals plus a. And I don't remember what my wording says. You're solving it for energy negative. What's different about this compared to the problem we just did?
There's two.
Right, there's two, which means you have two boundaries and three distinct regions.
Right.
So you're going to find the solution to the Schrodinger equation here, here, and here. Okay, my color choice failed me. I could fix that in a jiffy. So you're going to find three solutions, and then you're going to apply boundary conditions at each boundary. And of course, your boundary conditions are twofold. Number one is that psi 1 has to be psi 2 at minus a, and psi 2 has to be psi 3 at plus a. Number two is, because this is an infinite well, you don't have continuity of the slope. What do you have? I didn't hear still.
What?
I couldn't hear what your answer was.
No, what did you say originally?
Oh, I asked, what is our second boundary condition, right? First boundary condition is psi is continuous. What's the second one?
The derivative is continuous except for when it goes to infinity every.
Change in slope is equal to, what do we get? Changes, I've got to go back to it because my memory's just that long. We got the change in slope is equal to 2m alpha over h bar squared. And you're going to have, this part here won't be as simple either. I know, happy times. Actually, no, it will be. It will be, because you can use the, at the boundary, you only have one term in region 1 and only one term in region 3. You'll have both terms in the region 2 because your boundaries don't go to infinity. So you're going to have a total of 4 constants, 2 for the middle region, 1 for each of the outer regions. So you have to apply this condition as your second boundary condition at each boundary. And then you have a fun, joyful experience of matching up and solving your 2, 4, 6, yeah. It should be 4 equations for 4 unknowns. And then you normalize it, and then you have some questions about, the energy states, how many energy states do you have, blah, blah, blah. So, yeah, once again, if you have questions, feel free to contact me. I'm more than willing to help. Now going to a second case with the delta function. What if we had a positive energy? So we're still going to have the negative boundary, a negative delta function, but now we're going to have a positive energy. So that means if we were to draw our situation, here's the energy. There's, potential energy is 0. And so we have our negative spike. So in this case, I talked about this last class period. You fly an airplane over the Grand Canyon, what happens? Nobody cares. It doesn't make any difference. So we're going to look at the same problem in a quantum physics realm. So once again, the Schrodinger equation, simplifying again, what's different? There is nothing different above this line. What is different is, well, there, above that line. What is different is instead of defining kappa as the square root of minus 2me over h bar squared, we define k as the square root of plus 2me over h bar squared. And the reason is very simple. Before we had e was a negative value and we wanted to have kappa being real. Now we have e as a positive value, we want k to be real. And so the minus sign not inside to keep it real. Solution still has to have this form, so let's plug it in. So if I take the second derivative, this time I'm not going to go through in gory detail. What do I get for the second derivative?
B squared b bx.
Or just b squared psi is the quicker way of writing.
Side.
So plugging that into my Schrodinger equation, I have b squared psi equals minus k squared psi. Or being very pure mathematically, b squared plus k squared times psi is equal to 0, which is true either in the trivial solution, which I told you like first or second day we never use. That is when psi is 0 and we have no wave function. Or when b squared minus k squared equals 0, therefore b is equal to plus or minus the square root of minus k squared, which is plus or minus ik. So we have two solutions, but go ahead.
The first, it should be b squared plus k squared, the first thing, right?
Yes, thank you.
Okay, yeah. Make sure.
I'm going to at least pretend that I meant to write that and somehow my pen didn't record. We'll pretend. Okay, so now we have two solutions. So our solution is going to be psi is equal to a e to the ikx plus b e to the minus ikx. That'll be psi on the left side and psi on the right side. Oh, I should use the signs the same as the textbook does. So there's our solutions on the left-hand side and the right-hand side. Or I could have put them in sine and cosine if I'd wanted to. So we've got our solutions. Now what?
You have to find the coefficients.
Okay, now we got to try to find a way to find the coefficients. There is a problem, though. Do you see the problem?
We have the left side of the wave function is from 0 to negative infinity, right?
Correct.
So that means that on the left side function, the negative ikx goes to infinity,
No,
right?
because of the I. The I makes it sinusoidal. But you're barking in the right direction. If it's a sinusoid going on forever, that's a problem. It's not normalizable, right? So we have that problem again. Hey, this is not normalizable. This is not something it's not really a quantum solution. It's still something that's useful. So, yes, here, oh, wait. Oh, no.
I read it first time.
Yes. I had a teacher when I was in college, when he'd make a mistake, he'd be like, oh. Okay, so we now go on to applying the boundary conditions. And so at the boundary, at x equals 0, we have it's continuous, so a plus b equals f plus g. And then we have the slope is not equal, the slope is not continuous. We have our boundary condition that the change in slope has to be minus 2m alpha over h bar squared times psi of 0. And so that gives us this. There's our second boundary condition. Notice the a, b is equal to fg from up above. It's not two special ones. It's just there's two different ways of writing the same boundary condition. Okay, I'll stop thinking I'm funny. We really can't do anything with that. But we can recognize that this is just the position portion of a traveling wave. If we were to put the time portion in, we would have this here. Those are opposite signs. What does it mean if we have opposite signs in the exponent there?
To the right.
It's going to the right, yes. I'm going to have to go back and give him credit on that quiz question just because he's totally got it.
That's right.
So it's going to the right. This one here, same sign, going to the left. So we have one to the left, one to the right on the left-hand side. Likewise, one to the left, one to the right on the right-hand side. So we can define these as A is the amplitude of the wave traveling to the right on the left side of my boundary, and B is the amplitude of the wave traveling toward the right, and F and G on the right-hand side, same things. So we can interpret these for physical meaning. So now we can talk about a scattering problem. So the way my brain processes these is to go back to a wave on a string. I start with a wave coming in from the left. It hits the boundary, and I can have two things happen at the boundary. What are the two things that can happen at the boundary?
Go through the boundary or bounce off the boundary.
Right. It can be transmitted or reflected. And so in that case, and that's the exact case we're going to do, I would have two waves on the left-hand side. The one that I started coming in, and then the one that reflected back. So A is going to be the one I start. That's the one I control, right? I'm sitting here going, no. And then B is the reflection. And F, traveling to the right on the right-hand side, is the transmission. And G, 0. G, 0, because I'm not going to have a wave coming in from that side. So what I've done is I've taken this solution, said, let's look at a particular case. Right? This isn't the general case. This isn't like, oh, that's what this means. It's looking at a particular case. What have I done by doing this? Well, I've made one my independent amplitude, and then I have two dependent amplitudes, the one for reflection, the one for transmission. So I only have three variables, and only two of them are independent, one of them is dependent. Or excuse me, only one of them is independent, two are dependent. So with those definitions, now we can go through, okay, I do have time for this. We can go and we can solve, we can solve for what B and F have to be in terms of A. So you being the students, how should I go about solving this now? I want to find these two equations. How would I go about it?
But you want to get to those equations?
I want to get these exact two equations. That one and that one. How do we do it?
You go back up.
Yes, because I'm definitely going to go up to here.
So we know G is 0.
Yes, so I'm going to take these and just say for our special condition, that's 0, that's 0. Oops, turn off the auto shapes. That's 0.
Did they define the K as beta down at the bottom?
Beta is actually defined with simplicity right here. If we take everything and we divide everything by IK, then we have beta. Actually, got to include the minus sign. Since it has the I on the bottom, the same as having a positive I on top. I'm pretty sure that's it. Oh, nope. They didn't factor out the I. Didn't factor out the I. Just 2m alpha over, oh, didn't factor out the 2 either. M alpha over h bar squared k. So that's the beta.
So they're solved in terms of A. Yeah.
So I'm going to rewrite this equation right here with beta. So I have
So at this point, we just solve for whatever they had solved for down the bottom. Right?
right now we want to solve for any ideas yet?
For where it's F minus A plus B,
Yeah.
plug in A plus B for F itself.
That's right. So this will become now you notice the A's subtract out, and we're left with 2b equals minus 2 beta over I A minus 2 beta over I B. Any genius knows to cancel those 2's. And now what do you do? We're one step pretty much away here.
Add B over and then factor it out and divide by 1.
And then we also know that any math teacher would actually probably throw darts at your eyes if you left your answer like this, because you have 1 over i's everywhere. So multiplying top and bottom by I, you have equals I beta over I minus. Seriously? You have beta over I minus beta. That looks more like it. Did I do that right? I'm not feeling super confident in myself, but I mean, what could go wrong? That could go wrong. What's a couple signs between friends? So let's check.
Yeah, that's right.
B is equal to minus beta over I plus beta.
Except that's not equal because it's a minus.
Oh, and they multiplied everything by I once again. By minus I. So I multiplied everything by minus I. So minus beta became plus I beta. I became minus I squared or plus 1. And beta became minus I beta. So there we've got B. Now that we have B, now we can, well, what's the next step? Yeah, just plug it back into this equation here again to solve for F in terms of A. What I got my signs wrong again. I plugged in this one instead of that one, which is not technically a big problem, except for it's not going to give me the same. I don't want to go through and have to figure that again. Plus. Okay, so that's going to be the way that we have it down there. So now we have F and B in terms of A. Still not normalized, right? But we have something that tells us about the transmission and the reflection. So we can calculate then the transmission coefficient and the reflection coefficient. Notice that B plus F is equal to, well, B plus F is not equal to 1. It's the magnitudes that is equal to 1. The reflection coefficient is going to be B mod squared over A mod squared. The transmission coefficient is F mod squared over A mod squared. So I can just take what we found for B, take the mod squared. So That's calculating the reflection coefficient in longhand. And on top, then you're going to have minus I squared beta squared minus I squared is plus 1. So on top you have beta squared. On bottom you have cross terms, of course, are going to be 0. And you have 1 squared minus I squared beta squared. So 1 squared plus beta squared. So there's our reflection coefficient. And then our transmission coefficient is same thing, except for you're going to have 1 on top. It would be ridiculous to do the work again, but we know we're just going to have 1 on top. And then if we add the two together, the transmission plus reflection is 1. That's the thing that's 1. Because you have something coming in and you have two going out. Now, what does this illustrate? Well, it illustrates that we can do some math and that quantum mechanically, if you fly your airplane over the Grand Canyon, you're going to have some scattering back as well as some transmission, which didn't make any sense at all in a classical world. But in a quantum world, sure, yeah, beauty. Okay, hey, look, we're pretty much right on time. So doing this problem, you should be set for it. It's going to be the same types of things that we've done in today's lecture. It's more difficult than anything we did in today's lecture. It's not super hard, but it's more difficult than anything we did in today's lecture.
The face you had while saying that was good.
well, good.
It's more difficult.
Go ahead, Chris.
Question about homework.
Yeah.
For the first problem, we're showing or we're proving something, and in the hint it says to use the flux conservation.
Mm-hmm.
What is flux conservation?
Okay, so flux conservation is that it's actually very related to what we just did here. That your reflection and plus transmission has to be 1. The flux coming in has to equal the flux leaving.
But what is that expression of? I don't remember.
We did it in a homework problem.
Was that the first one?
Yeah, I think so. What does this mean? Andy said, frankly, I don't know what this means. Which, okay. The second actual one is yeah. And so, yeah, not that. Consider this wave function. No, not that.
Was it the first one?
No, because the first actual one was just the one where I gave you the solution and you just had to.
The first question from the second homework, did we use flux for that? Or that was the probability.
Yeah, I don't. It's not that problem. It's clearly not that one. And yeah, not that. So it's got to be in the third one.
Is it?
Yeah, this one here.
Yeah. Okay.
And so flux conservation is going to be, the flux in is equal to flux out. So the flux on your left side is going to be equal to the flux on the right side.
Right. So the coefficients, like the A and B, are those coefficients for the equations on either side. Are those like the probability, quote unquote, of like the particle coming through or being reflected back?
Yes.
Yeah.
All right.